Hey everyone, and welcome. Today we are going to pull back the curtain on one of the most powerful tools in all of computation, the matrix. Now, I know it just looks like a simple grid of numbers, but trust me, it is the secret engine that powers just about everything, from stunning computer graphics and network analysis to solving problems that seem, well, impossibly complex.
And just to show you what I mean, let's kick things off with a puzzle. How would you find the 1000th number in the Fibonacci sequence? I mean, sure, you could write a loop and just chug through them one by one, but that's 1,000 steps. What if I told you there's a way to find the answer almost instantly in about 10 steps? That's the power of matrices. Stick around, and I promise I'll show you exactly how it's done.
Okay, let's dive right in. To really master this tool, you gotta learn the basic controls first, right? So we're gonna walk through the fundamental operations step by step, covering everything you'd need to know for any computer science exam. So first things first, what even is a matrix? Well, put simply, it's just a two-dimensional array of numbers. Think of it like a spreadsheet, really. We always describe it sized by rows first, then columns. So a 3x4 matrix has 3 rows going across and 4 columns going down. And we can pinpoint any number inside just by its address, A and then row, column. So A23 is the number in the second row, third column. Easy enough? Now, here's a special type of matrix you're going to see all the time. A vector. A vector is just a matrix that happens to have only one column. Don't let the simplicity fool you, though. Vectors are the fundamental building blocks for representing points in space, the starting conditions of a problem, you name it. The transpose is another really straightforward but super important operation. All you do is you flip the matrix along its main diagonal. That's the one that runs from the top left to the bottom right. The rows become columns, and the columns become rows. So the element that was at position ij just moves over to ji. That's it.
A square matrix. Well, it's exactly what it sounds like. It has the same number of rows as it has columns. Now, this might seem like a small detail, but it's actually a really big deal, because many of the most powerful things we're about to do, like finding matrix powers or determinants, they only work on square matrices.
The basic arithmetic is pretty much what you'd expect. To add two matrices, they've got to be the exact same size, and then you just add the numbers in the matching spots. For scalar multiplication, you just take one single number, we call that a scalar, and you multiply every single element inside the matrix by it. All right, here we go. This is the big one, the operation that unlocks everything else, multiplication. Now listen closely, because it is not element by element. First, a classic exam check. The width of the first matrix has to equal the height of the second. Got it? Okay. So to find the value for a specific spot in your result, say at 1, 1, you take the first row from matrix A and the first column from matrix B. You multiply their corresponding elements, and then you sum up the results. It's this kind of row-by-column dance, and getting that rhythm down is absolutely key.
Now, this slide is super important because it shows the rules of the road. Matrix multiplication is associative, which just means if you're multiplying A, B, and C, it doesn't matter how you group them. But, and if you remember one thing, let it be this, because this trips everyone up. It is not commutative. A times B is almost never the same as B times A. The order you multiply in is absolutely critical. And to wrap up our basics, let's talk about the identity matrix. The easiest way to think about this is as the number 1, but for the world of matrices. It's a square matrix with ones running down that main diagonal and zeros everywhere else. If you multiply any matrix by the right-sized identity matrix, you just get your original matrix right back. It's the neutral element for multiplication. Okay, so we've learned the controls. Now let's actually use them to solve that Fibonacci problem from the beginning. This is where all that theory turns into an incredibly powerful problem-solving machine. So just to recap the problem, the Fibonacci sequence is a linear recurrence. Each new number is just the sum of the two before it. The normal way to do this, calculating them one by one, is what we'd call O of n in terms of time complexity, which is just way too slow when n gets really big. We need a shortcut. And here it is. This is the solution, and it is brilliant. We can actually encode that Fibonacci rule into one simple 2x2 matrix. This matrix literally represents the transformation that takes one pair of Fibonacci numbers and spits out the very next pair. And what that means is, to find the nth pair, we don't have to do n different steps. We just take this one single transformation matrix, raise it to the nth power, and apply it to where we started. And the result? It's a massive, massive leap in efficiency. See, raising a matrix to the nth power can be done super fast using a trick called exponentiation by squaring. It runs in logarithmic time. So our solution goes from O of n all the way down to OK cubed log n, where k is just the tiny size of our matrix. We have literally turned 1,000 steps into about 10. That is the difference between waiting around and getting your answer instantly. But this whole idea of using matrix powers isn't just for number sequences, not at all. Let's see how this exact same concept applies to the world of networks and graphs, which is a huge topic in computer science. So, you can represent any network, or graph as we call it, using something called an adjacency matrix. It's a square matrix where the rows and columns both represent the different nodes in the network. We just put a 1 at position I, j if there's a direct path from node I to node j, and a 0 if there isn't. It's a perfect numerical map of all the network's connections. Now, here's the magic. If you take that adjacency matrix, V, and you raise it to a power, let's say V to the 4th power, the new matrix you get tells you something incredible. It tells you the exact number of paths of length 4 between any two nodes. Look right here. The number at V4, position 25, is 2. That means there are exactly 2 different ways to get from node 2 to node 5 in exactly 4 steps. It's just an unbelievably elegant way to understand how a network is connected.
And believe it or not, we can take this even further. We can actually rewire the very definition of matrix multiplication to solve totally different problems. For counting paths, the standard sum of products logic works great. But what if we wanted to find the shortest path? Well, for that, we want the minimum of all the possible path lengths. So we just replace the sum operation with minimum and the product operation with sum. By just swapping out the operators, the exact same algorithm now finds shortest paths. It just shows how flexible this whole framework is.
And here's one more quick, mind-blowing example, Kirchhoff's theorem. It connects another matrix property, the determinant, to graph theory. It basically says you can count the total number of spanning trees in a graph. That's kind of like the network's essential skeleton, just by calculating the determinant of a special matrix that you build from the graph. It's amazing.
So, we've mentioned determinants a few times now. Let's quickly define what they are, along with their close cousin, the inverse matrix. You can think of these as advanced diagnostic tools for really understanding what a matrix is all about.
Okay, so the determinant is a single number that you calculate from a square matrix. It tells you all sorts of deep things about its properties. The inverse, on the other hand, is a matrix that basically undoes the original. If you multiply a matrix by its inverse, you get back the identity matrix. And here is the crucial connection. An inverse for a matrix A exists only if the determinant of A is not 0. If the determinant is 0, the matrix is called singular, and you can't invert it.
All right, I know that was a lot, so let's wrap all of this up with a super quick summary. Think of this as your toolkit for thinking about matrices and for absolutely nailing any questions about them on an exam.
Here's what you absolutely need to lock in. Key concept number 1. Matrix power is your secret weapon for solving linear recurrences incredibly fast. Key concept number 2. Taking powers of an adjacency matrix lets you count paths in a graph. Now for the mistakes to avoid. Mistake number 1, forgetting that matrix multiplication is not commutative. A times B is not B times A. And mistake number 2, always, and I mean always, check your dimensions before you even try to multiply 2 matrices.
So, we've seen how matrices can solve complex sequences, analyze social networks, and even find shortest paths. They really are a fundamental language of computation. So the real question is, now that you have this incredibly powerful tool in your toolkit, what problems are you going to solve with it?